That's a collaboration between our group at the University of Washington, started by George Lake, the N-body shop, and the Parallel Programming Lab, which is in the Department of Computer Science at the University of Illinois, led by Sanjay Kale. And what I want to talk to you about today is, well, first a little take on my take on the need for exascale, and talk about using other things besides MPI to program exascale machines, and see how that does today, and some perspectives for when we get the exascale, and if I have time, how that works on GPUs as well. Okay, so why do we need exascale? Let's start with what we're doing today. Our group is focusing on galaxies, which we lovingly do one at a time at extremely high resolution in the middle of a cosmological context. And you saw many examples of this yesterday in these zoom-in simulations. Try to be as physically motivated as possible. I'm sure Richard will take exception to this, but maybe it's just dimensional analysis at this point. But try to stick in the subgrid effects of star formation and feedback. Run the simulations all the way to the present, the whole 13 plus gigayears. And then, actually, the kind of thing that Alex is talking about, you know, these simulated observations, the data processing to analyze them the same way that an observer would. I'm sure most of you know about the stuff we published. We have done a good job of matching observational results, emphasizing the importance of baryons. Right? Some of my best friends are baryons. I think they're important. Yeah, there may be some that aren't. Yeah, okay. Yeah. And, you know, recently, just to summarize some of this is work that a graduate student, Farah Munshi, has done, matching the essentially the star formation efficiency, something that Richard talked about 2 days ago. In this case, looking at the stellar mass content as a function of halo mass. The observations are the green line. And one of the points that Farah makes here is that in order to get a good match, you have to look at the simulations the same way that the observers look at the galaxies. You've got to actually do a multi-wavelength observation, use those colors to get inferred star formation rates, take into account the surface brightness cuts at a Petrosian radius to fall on that line.
So you're saying the observer is missing essentially a factor of almost factor of 10 in stellar mass at around 10 to 12.
Yeah. Yeah, and it's sort of two things. The color to star formation, color to stellar mass content calibration depends on what you assume about the star formation history. And also, yeah, you're missing stars when you make a surface brightness cut. And then now going into detailed morphology of galaxies, Charlotte Christensen implemented a more sophisticated star formation algorithm. We're not just looking at the dense gas, we're looking at the molecular gas. This is something that Nick introduced, but Charlotte went to town with it in our simulations. And what she pointed out is that this introduces a very clumpy feedback, which is able to blow out a lot of the low angular momentum gas, and what you're left with is a higher angular momentum such that you have rising rotation curves, and that if you look at the bulges that are left, both in terms of size, here's the half mass radius as a function of h magnitude, And the brightness, this is the absolute magnitude as a function of, sorry, this is surface brightness. It falls on, these are Charlotte's galaxies in the red, falls on the blue points, which are the observational observations by Fisher et al. Okay, so this is nice for the galaxies done one at a time, but observers actually can estimate the scatter in this. And we can't predict the scatter if we're doing galaxies one at a time. We need a full sample. And so to do that, we really need to do that kind of resolution, but in a volume. And so here's the simulation I'm working up to now. Do an entire 25 megaparsec volume at that kind of resolution so that we can do these more statistical studies of what's going on with connecting galaxies, both in the Hubble deep fields with galaxies today and statistics of surveys. And I'll point out, this is sort of the bare minimum we need to do, right? The volume's too small, the resolution's kind of we can do better. I think we can do better subgrid models without having to do the full exascale simulations, sort of building on the stuff that Richard talked about. Instead of doing individual supernova, which we can't quite resolve, well, the supernova from a star cluster will combine to make one big bubble, which is essentially a pressure-driven snowplow where the interior temperature is regulated by the stellar output and the thermal conduction. And we can actually, James Wadsley and his student Ben Keller have demonstrated that you can actually follow this physics with roughly 1,000 solar mass particles. Okay, so if we go down to that resolution, we can include this kind of feedback. And then, but we still need the bigger volume. So this instantly gets you to exascale, get that higher resolution, get a reasonable volume that's still somewhat small compared to the galaxy surveys. But this is what you need if we're going to do, I mentioned nonlinear biases in galaxy surveys. If we want to do cluster stuff, again, the volume's kind of small, but relating galaxy clusters to, say, SZ surveys. So that's what we want to do at the exascale. How are we going to get there? And now I want to talk about programming languages. Okay, so most people have been talking about MPI codes in this conference, and a lot of people have gotten very good performance out of them. And when we get an exascale machine, it will have MPI on it, right? Because some lab is going to pay a lot of money to a vendor, right? And that vendor and it's going to have an acceptance test, which will probably be MPI. Okay, so there's sort of this, it will be there. However, MPI might not be the best match to the kind of architecture it is. Particularly shared memory doesn't actually match MPI. Certainly GPUs don't match the MPI paradigm. And, you know, just the concept of send message message from processor X to processor Y sounds an awful lot like move floating point value from register X to register Y. Why should I care about the number of processors on my machine? I don't know quite exactly how many registers are in my core. Why do we have to think so low level? And we're essentially programming these machines in assembler. All right, let's go the other way. From the high-level language, the point of a high-level language is to abstract all that detail away, hide it from you, and so that you don't have to worry about it, and all you have to worry about is your algorithms. a language will also give you performance tools so that you can understand the performance, not in terms of the messages sent, but in terms of these higher level abstractions, the same way that a debugger does for you on serial code. But sometimes, for example, an array-based language is going to be difficult to write a tree code in. So there'll be a mismatch between the abstractions that the language presents to you and the algorithm. And so you might have trouble there. And then, yeah, you've got to learn the language, right? As J.R.R. Tolkien, you know, life is short, languages take a long time to learn. So is it worth the time to learn a new language? And furthermore, you know, during that time, will somebody like Joachim or Volker come up with some new clever algorithm that makes all your work obsolete? However, right, I want to make the following point, right? Joel put this slide up about this comparison. I want to give a shout out to Paul Ricker, others that have participated in previous. There's people here from the Santa Barbara cluster comparison, Gus and Gustavo, right? Those have been very important for understanding the validity of the calculations we do. And I wanted to make the point, if we get the Exascale and there's only one code that runs on the Exascale machine, we're not doing science, right? There's this thing called reproducibility, okay? And so it's not just about getting Joachim or Volker to the Exascale. We've got to get a community of us to the Exascale if we're really going to use these machines to do science. Okay. So back to languages again. A couple of things. We do want a general purpose language. We want expressions that really are understandable for you C aficionados. And another important thing about a language is you want to know when you're doing something expensive, right? And this is key to easily writing high performance code. If something costs a lot, it should look expensive. And the other thing we want is sort of a modularity. There's a lot of code out there we would like to reuse if possible. So a language that will allow plugging in modules. Now, we could drop the general purpose, right? We could use a domain-specific language. And just an example of this, this is PhD work by one of the PPL graduate students, where he wrote a tree framework. Basically, you have a walk object and you have a visitor object that describes what happens when you hit each node. And he used that to write a Barnes-Hut algorithm and look at the performance. And you notice that this is on a Blue Gene queue, that he's able to take a 5 million particle zoom in simulation, the kind of thing that's hard to load balance, and get it to scale out to 4,000 cores, right? At this point, you only have 1,000 particles per core, and he's still getting good scaling. So you can be successful that way, but this is a hammer. If everything's a nail, you're golden, but everything isn't a nail, and so we need to go back to general purpose. And in general purpose languages, we ought to think about the hierarchy, right? There's a high level. I just added SQL, but I'm not sure if we're going to do N-body simulations in SQL. But it's a good example, right? This is sort of do what I mean, and you have a lot of magic that happens that takes care of all the details. The parallelizing compiler has been sort of a joke, but there are these languages that allow you to express your data dependence in ways that can work well. At a step down, if you, the user, can break up your program into independent objects, then you could have a runtime system that would map all those objects to your parallel machine, And that seems to be a sweet spot, right? It seems like everything in this conference has been at that level. And you won't have to worry about the scheduling and certainly not the expression of data movement, this parallel assembly. So Charm++ is the language I'm going to focus on now. And again, it seems to be very similar to what's been talked about before. And I came into, well, it came to my attention because it's been used by molecular dynamics community. Molecular dynamics, N-body simulation, Jonathan Coles told us about the similarities there. Perhaps it could work for me. So what it is a C++ based runtime system. You have a set of globally visible objects, and these interact by methods, and these methods are actually asynchronous. So go do something and I'll do something else, so that's the obvious parallelism. And the key to it is this sophisticated runtime system that maps those objects to the processors and then provides the scheduling and load balancing of the independent tasks. So more pictorially, you have objects, some of which are promoted to be globally visible. You can call, whoop, too fast. You can call methods on those objects, and those particular globally visible method calls are actually communication events in general. Okay, and so in terms of how you write it, it looks just like a serial code, except that these particular method calls generally invoke a communication. So the way you look at your program is this collection of communicating objects. The runtime system takes that, maps it to processors, and note, for example, when you do, let's say this. Sorry, I'm trying to get, say this object calls a method on this object. What actually happens is that there's the runtime system figures out where it is, sends a message across the network, and then sticks that message into a scheduling queue so it gets executed when there's time available on this processor. These tasks here are actually user-level threads. That means while you're messing with your data, nobody else is messing with your data. And that really, you can really write serial code and you don't have to worry about concurrency in most instances.
But how it knows how it is treated? How does the system know that, say, my C12 wants to talk to B0?
Okay.
And maybe all I'm doing is C1 is talking to B0.
Yeah.
And if it's system to different tasks, then I'm communicating all the time.
But, right, so first of all, right, so it has a database essentially, so it knows where that thing is.
I understand that that's how it works with it, but to optimally locate those objects, it requires some knowledge of who communicates with whom.
Yeah, so there's a couple ways you can do that. One is you could heuristically feed it some information that say if these objects are close spatially, then you might want to put them on the same processor. Or it actually can keep statistics of the communication and use that to, in a later stage, so, oh, these two objects are communicating a lot, put them on the same processor. So that can all be handled by the runtime system. So I wrote this code. We put together this code we call ChaNGa with the following features. Basically, the way to think of this is it's bug for bug compatible with gasoline, if you're familiar with that code. So the SPH is pretty much identical to gasoline. The gravity solver is a bit closer to PKD Grav 2 than gasoline, but those are pretty close anyway. basic data structure that we break up into the computation into is a TreePiece. I think Joachim originally came up with this. It goes all the way up to the root, down to a small collection of particles, say 1,000 particles or so, that are in a few buckets. I should point out, fault tolerance is something that ought to be taken into account by the run system. And so, just to remind you, right, currently, according to a recent user call, Blue Waters with 25,000 nodes, one node goes down every 8 hours. If we go up to a 1,000,000 node machine, it might not scale linearly, but assuming it does, you get one node failure every 10 minutes. And if your checkpointing takes 15 minutes to do, you're in trouble. So you need to do something sophisticated. And the checkpointing is a natural thing to do if your objects can migrate already as they go from processor to processor. Well, just processor to disk, not your standard checkpoint, or copy it to another processor so that if one node goes down, so you copy it to another processor. If node PE1 goes down, come on, I can continue the simulation using the copy of the objects that were on PE1. This is currently in the runtime system. Unfortunately, it's not supported by most batch schedulers right now. Right, usually, if you crash, your job's gone. But if this gets supported by the systems, this will work out of the box. There's even more sophisticated things you could do. Message logging. Sorry. Huh? Sorry, my machine seems to be stuck.
One of the,
Yeah.
Use the checkpoint.
Yeah. Sorry. Continue here. And then, and finally, load balancing, which actually which could interoperate with the checkpointing, because once one node goes down, you have to also redistribute the load. The way load balancing generally works is this principle of persistence. The load you're about to encounter will be very similar to the load you just computed, and so you can measure that load and distribute accordingly. With a typical cosmological N-body simulation, I got to modify that because I usually do a big step and then I do a small step. The load on the small step is very different than the load on the big step. And so we sort of save that load information. So when you do a big step, you go back and use the load information from the last big time step. So in terms of actually breaking up the computation into sufficient bits so that they can be scheduled properly and overcome communication latencies, we split it up into as many pieces. First, there's the tree pieces, the individual domains, and then even within a tree piece, we have an off-processor tree walk, we have the SPH tree walk, the local tree walk, the Ewald summation, this is all done independently. And furthermore, those bits, like the off-processor tree walk that requires data access, they get high priority. So schematically, it looks like this. The off-processor work actually goes through a Cache manager, it's sort of idea stolen from PQD graph, but this is actually a language feature now that was developed for our need. So if you have the data in this cache, you can feed it back, and this is because the off-processor data only needs to be stored for the processor. We don't need individual copies for each of the subdomains. So what does this look like in practice? So here's another thing. You get these tools to use to analyze your simulation when you have a language. So this is a time profile. So this is the percent utilization of the machine as a function of time, and the different colors represent various methods within the parallel program. In this particular case, this is the tree build here. The dark blue is the off-processor walk. The light blue is the local walk. The very light blue is the EWALD. And then SPH stuff is in green. And then the cache, so the communication load is sort of the red and the yellow and black. And of course, white is bad. That's idle time. Okay, and so you can see that, okay, as far as load balance goes, we're doing okay. There's maybe 15, 20% load imbalance. But notice the overlap we can do. This is the two-sweep SPH. So here's the first sweep. We get done the first sweep. There's a big, this is the second sweep where we calculate the pressure. And then we also have to integrate the thermal energy equation. And we can overlap all that work with the gravity calculation. Okay. How does that scale up? So this is a 2 billion particle simulation. It's a 25 megaparsec dark matter only at redshift of 0, so fairly clustered. Okay, and we're scaling out to 32,000 cores. The gravity walk calculation continues to scale. The total time starts to flatten out, and then sort of, let's do the dirty laundry here. The total time actually increases at 65,000 processors, not because the gravity walk is getting slower, but because some of this overhead is creeping up. So we can use the tools to examine what's going on there. So here's that utilization process profile again. Here we're going, again, 32,000 cores. This is roughly a 10-second time slice. And we see that the load balance is still pretty good, 15, 25%. But the setting up, this is essentially the breaking up into tree pieces. And this is the load balancing step. And so it turns out that, right, we've got, what, 200,000, essentially 250,000 pieces that we're trying to organize here. And there are some serial steps that were taken in here that became serious bottlenecks when I'm trying to, for example, sort out 250,000 pieces to figure out which processes are going on. But that's serial stuff that you can take care of, and we've indeed gotten rid of some of that. We still need to work on the load balance. This is 50,000 processors on Kraken, and so still doing better. Again, that's a serial problem. We're using one processor to figure out the load balance. It'd be nice if we had like a parallel language to do that. Wait, we do. Okay, so that's something that can be solved. All right, thank you. And just to show what the load balance issues are, so this is not the particles, these are the domains, all right? 250,000 of them that are colored by their load. And you can see that because we have a large cluster up here, well, it's probably less than a Virgo because this is but large for this volume, there's a serious load up there. And so when you do the load balancing, you see that more than half the load. So this is now colored by processor number. So half the load is in a quarter of the volume, and the load balancing is able to take care of it. 5 minutes. Well, let me just talk, going to Exascale. Let's think about our Exascale machine, and can we use it? We've got 1 million nodes. We've got 1,000 cores per node. Possibly get, and that'll give us 10 exaflops. What will running an N-body simulation do on this? So Abhinav Patel is another student of ChaNGa and did the analysis basically based on the ChaNGa data structures and floating point operations, calculate the total time to compute given a certain efficiency. That is, this is the quoted peak speed. We can probably only get 1/8 of the peak speed in a gravity calculation. Calculate the total communication time based on the number of messages, and if we're going to get an exaflop, the sum of those two times, the number of floating operations divided by the sum of those two times better be greater than 10 to the 18. You can do an analysis on the number of messages, assuming that each node is a shared memory machine, and so you only have to look at what the edges of that node are going to grab for the gravity calculation. You put all that together, and you can get the architecture constraints in terms of the message latency and the network bandwidth that you need to get a exaflop performance on a 7 trillion particle simulation. And of course, this depends on efficiency. Like I said, ChaNGa has an efficiency of about 1/8. So, so anywhere below, sorry, it has to be above this line. I don't know if Tom is laughing at me, or is this reasonable to have microsecond latency and say just under 10 gigabits per second bandwidth on such a machine?
Yeah, so
but
microsecond latency is pushing it. It is achievable by optimized InfiniBand and not quite Gemini. And I haven't seen the analysis on the newest stuff.
Okay.
But it's a good boundary condition.
Yeah. So the point here is that for doing Barnes Hut on an Exascale machine, this is a simulation I would like to do, right? This is this 100 megaparsec volume at reasonable resolution, and we're not violating causality. So that's a pretty good start. There are some assumptions there. In particular, what I learned about today is, or this week, is data movement. So we have to worry about that, and SPH is going to be a little bit harder because of the smaller float data ratio, but we might be getting there. 1,000 cores per node, we're probably talking GPUs. So I should talk a little bit about GPUs, but I'd rather answer questions. So yes, we can use GPUs, but in summary, I just want to say, I think we've been successful at this, although it's taken a while. Okay, we're 10 years into this project altogether, so a little patience. But we've used many of the language features to get very good performance. We did have our missteps. You really do have to think about, you still have to think about communications. Whether is better spending my time elsewhere is unclear, but I think I'll still make the argument, as we get to larger and larger machines, MPI is going to be more and more unfeasible, and this might be the way to go. Thank you very much.